Hello and welcome everybody to Power Channel TV, your weekly opportunity to spend a little time at Briggs & Stratton and learn about different technical topics and or administrative items as well. So what we're going to be working on today here is a continuation of our electronic fuel injection program here, where we're trying to give you a little more background here as to how to deal with some of these service items and kind of build a video library for you to work from as well. So this week we're going to be starting from the top of our diagnostic trouble code list, which is represented by P0031 and P0032. Okay, these have to do with your oxygen sensor heater system. Now, if you're working on a fuel-injected engine that comes equipped with a closed-loop injection system, so this is primarily going to be turf equipment, zero turns. So whether it be an 810 EFI Vanguard engine or a big block Vanguard engine in a turf application, you will find that it has an oxygen sensor in the muffler that is in charge of providing feedback to the ECM in terms of how the engine is using the given air and fuel ratio, and can have some authority to make some adjustments if things start to skew from a target number. Now, a lot of your marine application big block EFI engines do not come equipped with a closed loop system. They're completely open loop, so they have no O2 sensor in the system. You'll notice in all of our service literature it'll say if equipped when talking about these particular codes. Okay? So our hypothetical scenario is you get a machine that comes to you with the check engine light on, okay, or the MIL, malfunction indicator lamp illuminated, and you have read the codes and it's producing either a P0031 or a P0032. That indicates that you have a malfunction with the circuit in your O2 sensor heater. Now, let's talk about the O2 sensor for just a moment here, because I got to be able to explain to you and divide up the two different work duties being handled within that component. Now, the part we're focusing on today is strictly the heater circuit. The heater's job in that particular component is to bring the core temperature of the sensor up to anywhere between 600 and 900 degrees. That is the optimal operating temperature for that particular sensor. Now, exhaust gas, temperature, and all that will play a role in that. The computer is sensitive enough to look at resistance. As things heat up, the resistance will change. And it knows that it can taper or add a little more voltage, or current, I should say, to that heating element to bring the temperature in line with where it needs to be and basically hit a resistance target number. Now, the system is pulse width managed, so meaning the fact that the circuit for it is tapped on and off in a very rapid succession, sometimes up to 60 to 80 times a second. We gain a lot better finite control over that circuit that way. However, it's very hard to accurately test it. So we have some sort of crude, not crude, but more of an old school approach to just testing whether the circuit is physically working or not. You would technically need a device called an oscilloscope to watch the pulse width management function taking place. The other side of the sensor, which we'll cover in a later program, is the actual sensing side of it. Okay, the part that actually is monitoring the exhaust gas and reporting data back to the ECM about how the engine's using it. Okay, so with that being said here, our training board, or our engine in this particular case, will have a P0032 that has supposedly developed on this, and we need to start from somewhere to begin to diagnose this. Now, the service manual we offer for these engines, meaning the fact the EFI troubleshooting service manual, part number CE8182, that has very detailed flowcharts for each particular code, and when you run through this flowchart, it asks you a series of questions, and you have to truthfully answer these questions. If you decide to be cute and skip ahead, you're going to paint yourself into a corner very fast. You should be able to answer the questions and either answer yes or no to the results they're expecting. And that will either advance you or make you go back a step to figure out what was going on with that particular circuit. So one of the first things they're going to have you do is check for diagnostic codes, confirm it's actually there. So on our training board here, I'm going to go ahead and turn my ignition on, okay, and I'm going to go ahead and get my TinyScan code reader plugged in here and ready to go. And I'm going to read the codes. Now, it's telling me I have one diagnostic code available for viewing, so I'm going to read it, P0032. And by confirming this with the engine running, I will see that my check engine light is actually illuminated here on my miniature dashboard over here. Okay, letting me know that I do have this code is currently active, it's real right now. All right, so now we need to begin our procedure. So I'm going to leave the ignition on here because I'm going to be testing some voltage showing up to the O2 sensor heater. Now down here in this plug, okay, there's a set of 4 wires here. 4 of these wires are all used for the O2 sensor, whether it be the heater side of it and or the sensor side of it. So I'm going to be focusing on this red wire on the edge here and then this white wire with the green stripe in the middle as my main circuit for the heater. What I need to do first is I need to test to see that I have 12 volts showing up at this particular connector, okay? So first thing I'm going to do here is use one of my back probe wire sets here. You're going to want to use the one with the fuse in it. You are testing 12 volt power potential here. You do not want to short this to ground, otherwise you will create the scenario of the factory installed smoke and being let out. Taking care not to touch this alligator clip to this end of the board here, or anywhere that's a grounded material like the aluminum intake manifold or the engine block, etc. I'm going to attach that end to my red meter lead. Now I'm going to take another back probe pin here once I get my jumper wires ready to go here. I am going to now place the back probe in the dark brown wire on the outside edge here, okay, and that will give me a ground path. Now the other end I'm going to hook up to my black meter lead here, and once that's done I'm ready to take a voltage reading. Now if I come over to my meter here, turn my meter on to volts DC, I'm getting 12.6 volts available out of that red wire right now, which is good. That's perfect. We're seeing battery voltage there. Now if you don't see battery voltage, you need to back up a few steps here. So if we take a look at where our fuse block is located here, that's where you would end up starting. Okay, so if I back out here, and my fuse block on my training board is mounted over here in a corner, but the actual engine, it's mounted right over here, straight below the voltage regulator, which is right next to the spark plug on this side of the engine. Okay, you would remove the fuse block plug and you would look at the fuses in it. Now, you're going to have a set of fuses and a relay in here. This yellow fuse, which is the 20 amp fuse, this is the one you would be suspect of. Now, that circuit is in charge of powering things like our ignition coils, both our injectors, our fuel pump, all of those items. So those items will not work either if that fuse has been compromised. Okay. The other thing you need to look for, or at least inspect, is whenever you turn the ignition on and off, I should feel that this relay clicks on and off as a bare minimum test. If you feel it operating, it's probably working. However, that could impede current flow through the rest of those circuits, and again, you will not have functionality of the engine. It will crank and crank and crank and will not start because you are not getting any power to your coils or your fuel injectors at that point if that fuse is compromised. All that checks out. You need to consult the wiring harness schematic, again, in the service manual, and do a continuity check between this circuit here from this 20 amp fuse over to your O2 sensor plug. Figure out where the disconnect is in between that you're not getting 12 volt power there. Okay, moving on. The next thing I need to do is jump back over here and I'm going to disconnect my O2 sensor itself. Okay, and I need to inspect the pins. Now, when I'm looking at this, it's really hard to see in the image here. I'm trying to get the light to shine in the best I can, but there are a series of 4 male pins down here, okay? I need to make sure that those look like they're all at the same height and none of them are bent over, pushed out of the way, or there's no corrosion on there, okay? Some of the most obvious things here can bring this system to its knees, okay? So I don't see any terminal damage here. So if I look at my other side, which is, I'm going to remove my back probe pins here for a moment. If I look at my connector side attached to the wiring harness for the O2, I notice that I can't really see the terminals very well. There's this purple plug in the way here. That's a retaining clip. So if I take a small flat blade screwdriver, I can actually walk that out. There's little notches on each side of it that allow you to do this. Now I can look at all my terminals here and make sure that they're at the same height, they're not damaged, anything's wrong with them, etc. If all that checks out, our wiring here is probably okay. So I'm going to go ahead and reinsert my plastic retaining clip and snaps back into position. Okay, now we need to test the actual O2 sensor side of this, the heater. So I'm going to go ahead and plug this back in. Now, when I do this, I'm going to take my back probe lead here. I'm going to place one in the dark brown wire over here on the end again to pick up a ground path. Okay. And then my other wire, I'm going to back probe the white wire with a green stripe this time. Okay, because now I'm going to be looking on the return circuit back to the ECM from this heater. Hook that up to my red meter lead. So that's where I'm expecting the power to come from. The other one I'm going to hook up to my black meter lead since it's part of the ground path. Turn my meter on. My ignition is on. Volts DC, I see millivolts here. I see nothing. Even if I run the engine, I still get nothing. Okay, so that tells me I have a disconnect between my O2 sensor back to that circuit. I know I'm getting 12 volt power into it, but I'm not getting anything back out. So that tells me there's a break in that circuit somewhere. Okay, now the white wire with the green stripe leads all the way back to the ECM. And that is the wire that's responsible for telling us that, hey, I have a voltage issue here coming back to the ECM. Now, the code we're throwing, the P0032, when you consult the operator's manual, or the schematic, I should say, or the service manual, it will tell you that, hey, that indicates that you have low circuit voltage in this particular case. That means there is not enough voltage coming back that it's happy with. Now, the inverse of this is if you had a complete circuit through the O2 sensor heater but no resistance, okay, nothing to drop the voltage at all, you would see that same 12.6 coming back, and then you would set the P0031 high voltage. Okay, so again, the O2 sensor heater would have had to short to power basically and lose all of its resistance to set a P0031. Now to set the 0032, that basically tells us we have a disconnect somewhere. Voltage is not coming back on that white wire with a green stripe to the ECM. And of course, starting with the easiest things first here, we pretty much just proved our circuit is intact and working in the wiring harness. The ECM knows the difference here. It can tell. Okay. Now, the second thing we need to really check here is our O2 sensor. Now, the obvious thing to look for is any sort of burns or abrasion in the wiring and so forth. If all that looks good, you can confidently replace the O2 sensor. You're no more guessing or you're throwing darts and hanging parts here. You can confidently replace that and test it again. So ultimately, you'd put the new O2 sensor in, plug it in, clear your codes out with your tiny scan, go out and run the machine again. If the code doesn't come back within 15 to 20 minutes, you probably got a pretty good handle on it at that point. It's sharp enough to know that within that time frame, the code will come back if there's still a fault there. And then, of course, you'd have to dive into more of the advanced things then that the troubleshooting flowchart would have you check, like things in the wiring harness. And lastly, the last thing you'd ever end up doing is replacing the ECM. That is the most unlikely thing to ever go wrong with this. Electrical connections or just common component failures are the most common thing to go wrong. Now, the O2 sensor heater, not saying it's a normal wear item, but it does see the most abuse. You've got these constant heat up and cool down cycles here, and it wrecks the porcelain resistor in it over time, or if something strikes it, a tool falls on it, or the bumper gets smashed in up against the muffler, that concussion will break the heater element inside of it, opens the circuit, and now we end up with this 0032 low voltage code. Okay, so those are the most common things that will happen. Now, performance-wise, you really won't notice a big difference in engine performance. Really, the heater's job is to get this thing up to temperature quickly so that when the engine begins to use the closed loop function, i.e. the O2 sensor input, that it's at a proper operating range of temperature that will give us accurate results. If it's extremely hot or extremely cold, the results begin to wildly vary. So we need to keep it within a range here. Now, the engine will probably already be up to decent temperature, and your exhaust gas temperature will bring that sensor up to temperature within range, especially if you've been working it and cutting it grass. You're probably never going to notice a performance loss from it. But just know that it is a function of the O2 sensor. It does need to get corrected, though, if you want proper performance and the O2 sensor life to obviously last here. However, at this point, the O2 sensor is bad. It needs to be replaced. Question and answer session here for today's program. Question comes from Archie here in Maine. Why are there two codes again for this, and can you review what they mean? Excellent question, Archie. there's always two codes that are associated with every particular component failure here, okay? When it comes to a sensor particularly, they either indicate high or low voltage. Now, in our particular case here, our P0032 usually indicates a higher voltage in most cases. In our absolute case here, 0032 indicates low voltage. So if you picture a window of operation here, typically it's 0.5 volts to 4.5 volts. Anywhere in that range of 0.5 to 4.5 is considered normal. No codes become present. If you step below 0.5 volts for X amount of time, it's going to throw a low voltage code. Now, if you step above 4.5 volts for X amount of time, that's when it will throw the high voltage code. So that means you are operating outside of a normal window that it is programmed to look at, okay? So that's the reason why we have two different codes. Basically, it's just indicating which end of the spectrum you're falling off of there in that particular circuit. All right, Ted asks, what should we see for voltage on that white wire if everything is working correctly? The wire Ted's referring to is actually a white wire with a green stripe, and that's the signal returned back to the ECM for that heater. Now, again, that's not an exact science for measurement because it is, again, pulse width managed, but we can get fairly close or at least understand if there's a circuit. So when I tested it before, we got 0 volts. It's because we had no circuit through our O2 sensor. Now, if you test it normally, that voltage you should see drop from about 12.6 volts from the red wire, and you'll see a voltage drop down to probably high 11s to mid 11s for voltage. That would indicate to me that, okay, the circuit's been engaged and there is complete continuity through and there is resistance within the O2 sensor heater, and it's coming all the way back to the ECM at that point. That's when you typically will not have a code present, okay? Everything's satisfied with the amount of voltage coming back on that white wire with a green stripe. Only when we see 0 volts here, now it's stepped obviously below that 0.5 volt threshold here. And in this case, it's about 12.2 volts is the high end it will throw back, okay? And the low obviously is 0.5 here. All right, next question. Larry asks, how will I know if this part is bad again? Sorry, I missed the first 5 minutes. Larry, basically, the part that you missed is when we did a diagnostic rundown on this where we read the trouble code, okay? The check engine light was on the machine. I ran the trouble codes. It showed me I had a P0032 stored, okay? So that means that I had a code for an O2 sensor heater, and ultimately the P0032, I just followed the troubleshooting flowchart within the service manual and explained it on video here, and that's how we got to where we are with verifying the O2 sensor itself has physically failed. All right. Dave asks from Marietta, PA, you stated 0031 was high voltage and 0032 was low. I think you have that backwards, don't you? It's an excellent point, Dave. This is the only one in our system that's actually reversed. All right, and engineering has done that on purpose for reasons I don't know off the top of my head here. But yes, it is an excellent catch. Typically, the higher number, okay, so in this particular case, a 032, in normal circumstances, automotive, all that would indicate the high voltage side of it. And then the lesser number would indicate the lower voltage. In our case, in this particular code set, it's the exact opposite. So 0032 is programmed to show up if there is a low voltage code, and then 031 will show up if there is a high voltage code here. This is the only exception to that rule. Thank you for pointing that out, Dave. All right. Stephen from Antioch asks, how many total sensors are there in the system? Well, if we take a moment to count them out here, there's approximately 5, okay? Starting up here, a map sensor and what we call a T-map. There's a temperature sensor, a thermistor, and a map sensor built into one sensor component here, so those are 2, okay? I have the O2 sensor itself, so there's 3. And then I have what we call an engine head temperature sensor, or EHT. That's mounted on the #1 cylinder head, so that's 4. And my last one over here is our crankshaft position sensor. It's in charge of measuring crankshaft speed and counting teeth on the flywheel, so the ECM knows how to go about its duties of firing spark plugs and injectors. Consequently, there's about 5 components on the system too. You've got ignition coils, 2 of them, 2 fuel injectors. You have a fuel pump, and you also have the O2 sensor heater, and there's a relay inside of the ECM, or inside of the fuse block here, that also is ran by the ECM here and is all part of the circuit too. All right. Norman from Gloversville says, it seems to be too many codes for a small motor. Well, Norman, it's kind of geared after automotive here, where you could see up to 450 to 500 different codes in a car, just from the engine and transmission alone. So this is a little bit of a downgrade from there. However, 26 different codes, it would be highly unlikely you're ever going to be combating all of them at once. I would argue that you probably would rarely ever see that situation unless something is physically unplugged at the ECM and now it's going to throw random codes for the things that it sees missing. However, these are just the core things you absolutely need to run this engine. This is as stripped down as fuel injection as it gets, to the point where it's reliable and accurate. Now, there are lesser systems out there that do have less componentry on board. Cowie's DFI system, for example, far less complex than this. However, it doesn't give you the exact precise fuel metering, as well as spark timing advance, and also the closed loop feedback system here that we have in our system. All right, Kevin from Perth, Ontario. Will the wiring plug terminals be a service replacement part? Excellent question. Kevin, we looked long and hard at trying to make all the different terminals available, whether it be these Delphi GT connectors, the pins that go inside of them, the terminals themselves. You then have the seals, you got the locking clips, and then you need a special pair of crimpers and open barrel crimpers to do all this work. And the cumulative amount of different connectors and pin sizes here, it was about $300 US. And the entire wiring harness cost $154 to replace. So it was a struggle of, which one do I choose here? Probably the lesser route, considering the engine's covered under warranty for the first 3 years. If you find something that's permanently damaged, you just can't repair it right then and there in that wiring harness, it's best to just replace the whole thing. You're taking the liability out of it. You're getting paid to do that job for the first 3 years. It's a no-brainer. All right, Dave asks, is there a EFI service manual that has diagnostic help for conditions that do not represent any fail codes? Yes, there is. Actually, Dave, if you look out under the Briggs engine tab, and then you'll find technical resources out there. And then below that, you'll find EFI resources. There is a PDF of our part number CE8182 EFI service and diagnostic manual. So obviously it covers all fuel injection related stuff, but in the very back of the book, there is also a write-up of common things that can affect engine performance. The engine still reacts the same way as a carbureted engine that you're used to. If it's lean, it hunts and surges thanks to our mechanical governor. If it's rich, it makes black smoke out the exhaust. Or if it seems down on power, those sort of things. All of it can be attributed to the same mechanical faults like valve lash or other things that you've ever seen wrong with the basic 4-cycle engine that has a carburetor on it. Okay? All those things still manifest and show up the same way. But yes, to answer your question, there is a troubleshooting flow chart, where you list out your symptom, and then the possible conditions that can cause it are all spelled out in the back of that CE8182 Service and Diagnostic Manual. Again, it's found in a PDF form on the Power portal itself, on the Briggs Engine tab, Technical Resources. All right, that looks like the end of our questions list. I want to thank you again for spending some time with us here. I hope you learned something. And again, this broadcast by the end of the day or early next week will be available for view on demand, as in past episodes of the Briggs & Stratton Power Channel TV. Thank you again, and we'll see you next time.